Sometimes we read the news about the hybrid batteries used in Shanghai, China, and Germany to run the buses, railways, and so on. So these are some of the devices, which means that this device, this class of materials has a specific specificity that you can use this device as a power, as a capacitor, at the same time as a battery, because it falls between the two ends. Okay. Okay, just go next. I don't think it's working. It's working. Okay. Now, to make it little bit simple, see, if you look at the power, this is the power. It's a capacitor, and this is the energy. So if you have this coffee mug and a bottle, you will see that from even it has the same quantity of material, same quantity of energy, that can be finished very quickly. But if you have a control way, this energy can be taken out for a longer time. If the at energy is taken, so that power is taken for a longer time, then power into time will be the energy. That means this is the way how we can for a device in between these two. That means if you have more power, so that's why these are some of the electricity storage systems, battery, capacitors, and the supercapacitors. So we are looking for something here, somewhere here. Okay, next one. Okay, I think I can work it out. Okay, now in a very specific way, this gives the comparison. In fact, the comparison in a quantitative way. See, if you have a capacitor charging time is very fast. It's 10⁻³ seconds. It's microseconds. You can charge the capacitor. Whereas the batteries takes a longer time. Of course, even for your for the mobile also, it takes longer time. 2 to 3, 4 hours it can take for the charging, because you use a battery. So in comparison with that, if you see, and if you form a device with capacitor, supercapacitor, then you will see that the supercapacitors can be charged between few seconds. That means if you could make a device, you can replace the battery, but battery takes a longer time for charging. So if you replace the battery by supercapacitor, then charging will be very fast. So you don't have to wait for longer time. Even few seconds are sufficient to charge your supercapacitor, which also acts as a battery. And similarly, other way, discharging time for the capacitor is also very high. Fast charging, fast discharging. Battery also takes a similar time, depending upon the load in the circuit during the discharge. You will see that battery can be charged slowly and it can be discharged slowly. But supercapacitor can also be having an in-between place. So it can charge very fast, and depending upon the load, if you put more load, it can be a longer time. So energy density and power density. So capacitor has a very small energy density. Battery has very high energy density compared to the capacitor, and the supercapacitor has all the in-between handles. So the similar thing is the power density is very high. Here power density is low. But you can form a capacitor with the power density of 1000 to 2000. Now, these are some of the advantages of the capacitor. The life cycle is 500,000. That's 5 lakhs time. Here also you will see that the battery can be used. The battery life is about 500 to 2000 cycles. 2000 cycles. What does it mean that even if you have a battery in your in the mobile, probably after every 2 years you have to change the battery. Why? Because its lifetime is about 500 to 1000 cycles. That means you can charge it 500 times and you can discharge it 500 times, and then you have to change the battery because that's their life cycle. Therefore, what does it mean? That this will last at least for 2 to 3 years. And at the same time, the supercapacitor has a longer life, about 1,000 times, 1 lakh times that has been tested, which means that the battery can be replaced by the supercapacitors. So that is the way. This is the new class of the materials and the devices that we are going to explore, which can replace the with the battery. Okay, so that is the idea, because it has superior properties than the batteries. Okay, next one. Sorry, I think. Okay, now this is the status. What is the status now? Which type of materials are being used? Because we talk about the material scientist, and the materials which are used and useful for our purpose to form a batteries. Say most of the supercapacitors which are available in the market, they are based on the carbon materials. Carbon is very cheap, and but it exhibits a low specific capacitance. This is a unit to measure the capacitance. It is less than 200 cycles, but it is quite stable. Nothing happens to the carbon material. Other materials which are being explored are the other class of materials. There are the metal oxides, which has the capacitance values between 500 to 1000. Its stability is quite high. Another class that has been explored much more is the polymer-based supercapacitors. Since we are talking about the material science, we have explored most of the materials, metal oxides, polymers, so organic compounds, and also the carbon, a special class of materials. But you will see that compared to the carbon, we have to go for the other materials because it gives the low specific capacitors, even it is a stable materials. All the time, everybody will like to make a improvement in the device performance, properties, and so on. Therefore, the constant efforts are being made to have a material which can have the higher specific capacitance, and at the same time, it should be a stable one. The other factors which will also follow the cost of the material, whether it's abundant or not on the earth, and so on. Of course, you know that these materials are also available on the earth. So those can be used. Now, these are some of the requirements. Now, what do we want from this device? Because when you start for doing some sort of a research, we put a target before us, that we want to achieve that target. At the end of the research project, you like to have some target achieved. So what was the target? Capacitance greater than 500 Faradays per gram. So we are talking about the metal oxide supercapacitor or something like that. Then we also want a large potential working window, and energy and power density about 100 watt hour per kg energy density, and about 1000 watt per kg power density. If we could achieve from your material, from your device, this type of specifications, this type of results, energy density and power density values for your device, then this can replace the battery. This can be used as a supercapacitor in the market. And the durability, cyclic stability is 10,000. So you are looking for materials which are quite stable. 10,000 cycles is quite a large number. So you can use this material if somebody forms a supercapacitor And if it is charged, used as a charger, and you charge the supercapacitor used in the mobile, then about 10 years you don't have to worry about that one. So it will, durability will be increased, and at the same time it has all the properties which are of the batteries. But at the same time, the cost-wise it has to be cheaper one. So we are looking for some of the materials which also satisfy these areas. And for that purpose, what is a simple way, as experimental scientists, what we do, we select some of the materials, we put some of the criteria, and do starting the experiments on those materials and see up to what value we can reach, which is our target. So that's how we can go a little bit further. Now, the other things which are important for us. So this is our target. We want to have somewhere here. Here are the batteries. Here is also the capacitors. It's now the spelling a little bit different. And we want to have a value somewhere here. 100 watt-hour per kg energy density and 1000 watt per kg power density. So that's the target. So if you could achieve, if somebody in the world achieves this one, he will be the market. So this was the way we are looking for. And which type of materials we wanted to study. When we went to the literature, we found that these are some of the materials which are not explored so far extensively for the purpose of the supercapacitors. Because when you form a capacitor, it is basically the two electrode system in which we have anode and other is a cathode. And we have a electrolyte in between. So if you break the battery, a dry cell, you will see the same thing. So we need a anode and cathode material. So we want to make the anode and cathode materials with these materials. Now, when you make such type of materials, we can see that even if you make the material, what the form should it be? Whether you want to make a raw type, whether you want to make a powder, or you want to make a film over a large area. That means you make the material on the substrate itself, so that small material can be pasted or can occupy a larger space. This is known as the thin film. So if you could make a thin film of those materials, this can act as an electrode. Otherwise, you can have a pellet type of form. You make a pellet, you have a powder, you make the material, you just press it under hydraulic pressure and use as an electrode, as an anode or the cathode, depending upon the properties. So these are our requirement. And then we went a little bit further. So if you know, go a little bit further, you will see that these are the requirement of the supercapacitor electrodes. Many. We talk about the electrical conductivity of the material itself. It has to be higher. It's a logical one. Then the surface area, because the principle of storing the charge is the redox reactions. So if you have large surface area, more the surface, more reaction sites will be there. If there is a small surface, then the sites available for this reaction will be smaller. So we want a large surface area. We want that its electrical conductivity is also high one. Then corrosion, because we are using the electrolyte, so it should not get corroded in the electrolyte. So there are many other things when you come into the context. And what important thing we are looking for, the control pore size. Because when you make a material with a pores inside, then when you have a pore, the electrolyte what we are using for forming a battery or a supercapacitor or the electrolytic cell, the electrolyte can go in that pore. And pore also has a surface area. So more pores, more smaller pores will offer the large surface areas. That means we are looking for a material, even it is in a thin film form, that it should have a high surface area. Surface area has to be large. Larger the surface area, larger reaction sites will be available, and therefore large redox reactions can take place, and charge is stored through the to these redox reactions. So this is the basic requirement for us. So we want to make a material with all this commitment. That means we are not looking for a very uniform shape and size material, very compact material. We don't want a compact material. Now to make the such type of materials, or the materials depends upon their applications. If you want to use any material for the optical purpose, then the physical methods are used where the material is evaporated or sputtered, and where these are the costly affairs. But we are looking for the methods by which you can make the material of our desire. Our requirement is not a good material, good looking material. If we have a porous material, if it is a amorphous or nanostructure material, all the ways by which it can offer a large surface area, that is our requirement. So it has a pore, it's okay. Pore material may not be useful for the other applications in the electrical conductivity studies or electrical devices, but for us, that is not the requirement. Okay. The another requirement, what we are talking about. Okay. Is the preparation of these materials. Now we are preferring the chemical methods. And of course, I think most of you know the chemical methods. Those who are working on the different little projects at the college levels, though these are very simple methods which can be practiced at the college levels. And college students also can take the projects for the making the materials for the supercapacitors. So these are our requirements. We need the materials. Our methods are economical, easy, very simple methods we want to use. We want to use the materials on very large surface area, and we want to use the metal sulfides, not the metal oxides. Metal oxides have been studied and they are being studied in different compositions. New class of materials are coming up. We are not talking about that one. We want to explore a new type of materials, metal sulfides, because the sulfides have more electrical conductivity than the metal oxides. That's the reason. Okay. So some of the materials are toxic, some of the materials are costly. See, for example, the well-studied material is ruthenium oxide. It has the highest results, you can get it, but its price is very high. That's what the Professor Patil was also insisting. Look at the price. You make a material with the ruthenium oxide, the cost is very high. Compare to the material, the other material, which is manganese oxide, the cost is very low. So if you make a sulfide from them, you will use the same chemicals. So we are looking for the materials which are also economically not much costly. And at the same time, this is the sum of the materials, and also all the rare earth materials, they have the multiple oxidation states. Particularly, the rare earths have 3 oxidation states, which are quite useful for storing the charges. Our purpose is to store large number of charge. Okay. Okay. So this is the information about the materials what we want to study. At the same time, we want to make it like this. Then you will find that the graphene oxide will help in increasing the surface area, providing good also which is deposited based on this rare sulfides. At the same time, it is hydrophilic. These quantities are also required for us. This one. So the combination of these two, these materials are not much costly, and you can form the material in the thin film form. and it can satisfy all the properties which are looking for. So we want to make these materials in different forms. At the same time, when you go for the device, we already decided that we will go for the solid state devices, not the electrochemical devices. Because when electrochemical devices, we use the liquid or electrolyte for making the device, where there is always a possibility of leakage. So we want to avoid that leakage. We want to come out of that problem. So what we decided to go for the polymer gel electrolytes. And the another thing of that electrolyte is that it acts as a separator as well as an electrolyte. So what we are doing, we have the anode, one plate, another is a cathode. It's a parallel plate combination which we form in the capacitor. And in between we have the dielectric. Instead of putting the dielectric, we put our polymer electrolyte there. So it's an electrolyte. At the same time, it doesn't allow to short circuit. That means the anode and cathode are set at a certain distance because the polymer layer is in between. And then make a compact device. So it's a very simple device. You have one material, the another material deposited on some substrate and holding them together by putting some electrolyte in between as a polymer in this case, and then fix it. And that will act as a supercapacitor. So it's a very simple thing. That's why we have decided to go for the polymer electrolyte. Of course, these methods are quite known. I think I will just emphasize the importance of this method, and I always do when I go to the college, because for making the materials, you don't have to go for the sophisticated instrumentation. Even few beakers and frame form chemistry is sufficient for you to make your material, because chemistry friend will give you some of the chemicals, and if you have few beakers, you can make your own material. This is a very simple methods that we have developed, and we were working for about last 40 years or so, and we are advocating the same methods. We are quite successful in forming the devices also using very simple methods. It's a very simple method. With a simple beaker, you can make your own material. What you need? The chemicals. We don't have to go for a system. Generally, the films are made by the physical methods. One of the famous methods is vacuum evaporation, which costs about 35 to 25 lakhs of rupees to get that instrument. For us, even plastic beakers will be okay for us, which costs few. Or if you go to the other side, you can also use the plastic mug if you want to make the deposition. It's a very simple way of making the materials. What we do in a simple way, that, for example, in this case, is a chemical bath. We put chemicals inside. For example, in this case, I want to make a copper sulfide. The copper sulfide is a very good material which acts as in different fields. It's also a good material for the supercapacitor electrode. It can also be used in the catalysis activities. You can go for the hydrolysis of oxygen and hydrogen. Water splitting is possible use this material. So what we do, we put the materials, the copper, the cobalt sulfate and thiourea. Now these are quite cheaper materials, easily available. Put them together and put your substrate inside, and just heat it sometimes, or even at the room temperature. If you allow it for reaction to go, after some time you will see that a film is deposited on this glass substrate or stainless steel substrate, which means that you have made a semiconductor of your own. Making a semiconductor, and what we have in our mind is only the silicon. That we are doing it for the class 10th or standard onwards, and all the time talking about the silicon and its impurity, putting the indium and putting the group 5 phosphor material for making the N type and P type. That's the only we have in our mind. But it's also a semiconductor. It also shows the semiconducting properties. It's a good material for the supercapacitor. It can also be used for the water splitting. It's a good catalyst. So this can be used for some other purposes. And if you make this material in this form, that means that you don't have to collect the precipitate. If you have a precipitate, if you dry it, but that is not useful quantity for us, because when you make anode and cathode, you have to paste that powder or that precipitate on any conducting substrate, which is again a problem. Then you have to use the methods which are properly known as the doctor's blade method. You make a paste with some binder and just apply it. But since you use the binder, its conductivity changes. But if you make a material as it is on your substrate itself, then this substrate can be used for different purposes. You take this substrate out and use as an anode in your supercapacitor. So it's a simple way. So even small projects can be taken at the college levels, maybe by chemistry and physics departments. And its applications are tremendous. If you could have the facilities of this, making this material, then you are basically forming the materials for the supercapacitors. The application for which you want to go is something different. But making material and having the material of your own is very important for us. So if you have your material, then you can think of using in different applications. It's a semiconducting material. So just by forming a photoelectrochemical cell, you can study its photoelectrochemical properties. It's a solar cell material. It's having the band gap. Okay. And the another way of making the material is also a very simple one. Here we have 4 beakers in which you can get the copper. You can get the cobalt sulfide, and in this beaker you can have the thiourea, and there are 2 beakers in between, which is with the double distilled water just to range it. And this is a cation and this is the anion solution. So from cation we will get the cobalt oxide, cobalt CO2 as a adsorbed material. You dip in the second beaker to remove the excess quantity. You dip inside here, the reaction will go, and I will go for the reactions also. And then this material will react, the anions will react with the cations, and it will form a insoluble compound. So once compound is insoluble, it will not redissolve in the water. So basically, in that case, that material will be deposited on the substrate. And you repeat it many times, and you will see that its thickness increases. But in this case, you will get a material which is required for the electrodes. So these are very simple methods. Of course, there are many other methods, chemical methods by which you can make your material. And for this, you need nothing. In this case, probably you need 4 beakers. In this case, probably you need only 1 beaker. So you can start making your material in the lab, and then those materials can be analyzed. Of course, method looks to be simple, but results are quite different. There are certain parameters in this case. For example, what will be the parameters? For example, the concentration of the cobalt sulfate. If we change it, it will change the properties. Then we have put it on the magnetic stirrer and heater. That means we can change the temperature. Of course, if it is a water bath, we cannot go up to 90 degrees Celsius. Above 90 degrees, it will start evaporate. But you can change the temperature, you can change the concentration, you can change its pH, you can add some complexing agent to control the reaction. If you have control over the reaction itself, then you will see that the morphology, what is important for us and what we are looking for this by changing the preparative parameters is the morphology, basically the morphology. And I have already said we don't want a very beautiful morphology. We need very bad morphology for these applications. It's not a uniform morphology that we are looking for, but you can study the morphologies at different parameters, changing the concentration, changing the pH values, changing the deposition time also. You will see that if you take it film after 30 minutes, or if you take the film after 1 hour, its morphology will be different. So you can interrupt, you can take the films at different intervals and look for the morphology and look which is the better morphology for your applications. All these morphologies are required for different applications. So that's why if you decide your application where you want to use it, you can select the deposition thickness, you can select its pH value, you can optimize its concentration of the solutions and so on, and you can form your own material. I think maybe I can skip it because this is some other method I'm talking about, but I think I will skip it. Okay. I think. Look. So, I think I will just skip the discussion also of the same thing. Okay. Now this is a experiment I wanted to go because I have made many materials using the very simple method. So I will just explain one and then we just mention the importance of the morphologies instead of going for the details of the experimental conditions. You will see that the same thing is here. I want to make a copper sulfide. Where the copper sulfide is required? Probably you know that the earlier solar cells were based on the cadmium sulfide, copper sulfide. Cadmium sulfide is N-type, copper sulfide is P-type material. So you can make the cadmium sulfide using the same method. You can also make the copper sulfide using the same method. If you could make the layer one over other, you can form the junction also. A junction is possible. Junction can be made. A PN junction can be made using simple method if you deposit the other one material over other material. So this is the copper sulfide. This also shows the supercapacitor property that we know. Of course, I'm not talking about the details because this has 5 phases and which phases prepared at what temperature. I am not going to go onto those details. But you see what we have done. We have taken 0.1 molar copper sulfate here, and we have used triethyl amine as a complex reagent. Deposition is carried out at different temperatures. Time is same, which means that this experiment is done for changing the temperature and looking what is the effect of temperature on the morphology. That was the idea. So by keeping everything constant, 3 hours for the deposition, and using the very similar bath over here, and this is, of course, this is the reaction, how that film will be formed. You will see that just by changing the temperature and by keeping all the parameters constants. Of course, when you do the experiments, generally what we do, we keep all the parameters constant and vary only one parameter. We don't vary 2 parameters simultaneously. The parameter here, which we have varied, is the temperature. So this will affect, and you can see what is the effect of temperature, deposition temperature on the morphology. And you will see that in the next one. Yeah, look at the morphology. The first one, of course, there are different magnifications. You will see that what is the change at the same magnification. If you go on increasing the temperature, you see that the morphology also changes. Now you see that the morphology is not looking good. It looks to be a little bit ugly. It's porous. And even at the high magnification, you can some of the pores and the space in between the particles. Even though these are the nanostructure film, the agglomeration has taken place. So many small particles have come together and they have formed the bigger particles like this over the material. And you will see that all have the different morphologies. And this is the effect of temperature. That means if I study the properties, the supercapacitive properties, then I will see that one of the temperature, deposition temperature, will give the highest results for the supercapacitive properties. Then what I will do? I will select that temperature for the further deposition. That's how I can optimize the parameter also, and I can get desired morphology of my materials. So in this case, you will see that, of course, okay. Let's talk about the effect of temperature. Here also, this is the copper sulfide. The cobalt sulfide using the same thing. Here also, we change the temperature by keeping all the parameters constant. Everything is constant. But you'll see that the bath is quite simple one. Keep it for longer time. The reaction time was 12 hours. So you have to be patient sometimes. I mean, you put the reaction and go home. Probably if you wait that even in the 3 hours, nothing will come. And then you sometimes you pour everything without notice of others and just go home. But keep sometimes when you come to the next morning, you will see that the film is there. It takes longer time. Okay. So in that case, you will see this is the X-ray diffraction patterns, of course. Look at the morphology. Now, why we are looking for such type of morphologies? Because this will form an anode or a cathode. And when we put the electrolyte in between, then the electrolyte can go inside this part. If it is a compact one, if there are no holes, it's very uniform. A compact film is formed, then the electrolyte will not be able to go inside. But by making such type of films, we are increasing their surface area. As you know that when you talk about the thin films, you see that the geometrical surface area could be 1 by 1 centimeter square. Probably if I make a deposition over 1 by 1 centimeter square, this will be its geometric area. But if you go for its actual area, actual surface area, it could be 10 raised to 2 times or 10 raised to 3 times greater than the actual geometric area. And now, instead of that, we are also making some of the modifications by controlling the reactions, by adding some complexing agents. I can have a control over the morphologies, and I can get the different types of morphologies. So if you look to change in the morphology with the temperature, and this is at the highest magnification. You will see how morphology looks like at the magnifications. And I again say this is not a good and beautiful morphology for other purposes, but this is quite good materials and morphologies for our purpose. There are certain applications in which when you use a electrolyte in contact with such type of materials, these materials will offer the large surface area for reactions, because that electrolyte will go and make a contact with the surface, and it makes available the more reaction sites. So the reaction goes at very fast rate. So depending upon the applications, we need such type of morphologies. Another one, the manganese sulfide. See, because if you have chemicals, you can do wonders. Because the method is same. The method is same. Nothing is required. You need a material, a compound from the manganese oxide, manganese sulfate, manganese chloride, manganese nitrate, and the another one is the sodium thiosulfate, Na2S2O3, sodium thiosulfate. You need it, and you will see that even in this case, when we study for the effect of temperature, you will see that the morphology is quite different. Now here, it's very interesting to see the small cubes. The cubical morphology has been formed at very low dimensions. So it's a sort of a small crystals have been formed on the film surface itself. So there could be sometimes a fusion of these materials, and look at this case. How nicely these crystals have been arranged. Okay, let's go to another one. This is the MOS2. This one more material. It's also a good material for the supercapacitors. It shows the other properties like catalysis properties. It's a layer compound. Many applications that have been also used in the solar cell applications and so on. So it's also a good material. So you can make it, and you can also study the effect of temperature. You will see that the temperature, of course, we have the limitations from 303 to 333, but the morphologies. Okay, I think that I missed the morphology. This is one more material. This is tin sulfide. Tin sulfide, SNS. You can also, this time you can see the deposition time. Deposition time is different. You keep the other parameters constant. The temperature is constant, compressing agent is same, concentration is same, and you change the deposition time. But you will see that with deposition time, the morphology changes. Of course, I'm not going to do the reaction kinetics, what happens initially and how the morphology changes with time. But now we assume that the morphology changes with time, and you will see that this is the morphology what we get. Of course, not all morphologies are good for our applications, but we can find it, which is the best one for us. Okay, when we study the particular material. Okay, now we go a little bit further and talk about the rare earth compounds. This is samarium sulfide. Samarium is the rare earth material. Samarium sulfide. Not much studies have been done on such type of compounds and exploring its properties. Particularly, these are all semiconducting materials. So you know that all the semiconducting properties, if the band gap is between the say, for example, 3 to 2 electron volts, this also show the optical absorption. You can find this band gap. You can think of having studying its negative temperature coefficient and so on. So this could be one of the experiment in your text. You can develop different materials and go for finding out their band gaps also. So at the MSc level, I was doing the same thing. I was looking for the solid state physics laboratory, and we were making the materials. So for first semester, our students will make the materials using different methods. And then for further semesters, you will study the properties, because you have the expense to have to study the optical band gap of the semiconductor. And you have only one experiment. Probably you have only one film of cadmium sulfide, and everybody will get the same results: 2.4 electron hole, 2.4 electron hole. That's all. But what we were doing, we were asking the students to make their own material and then measure its band gap. Make your material on the glass substrate and measure its electrical conductivity. Instead of going the electrical conductivity of single crystal of a silicon, you have your own material. So even you can design many experiments, and you can enrich your lab, because if you put this as your samples, even in the experimental examination, factory examination, because students know this is the cadmium sulfide, the film is going to get, and I will get the band gap 2.4. But now you can get any type of film prepared by some other students, synthesized by other students, and ask him to find the band gap. So you can also enrich your laboratory by making different types of materials and use them for different purposes. Okay. So this is also one of the material. Of course, the other studies have been done. This is the samarium sulfide by using the other method. That method I will explain, and just I will skip this. This is the Silar method. Now we are using the 4 beaker methods. You will get a similar type of film. We get the SM2S3. But the morphology which is obtained by first method will be different, totally different than the morphology obtained by this method. So even if you change the method, instead of using one beaker and naming is a chemical bud deposition, if you use this Silar method, which is successive ionic layer and absorption method, you will see that the morphologies are different. So you can make the same material with different methods and make a comparison. And if you go to the literature, you will find that there are many reports having where the comparison of these properties have been done. They have compared different methods and to find out which is the best one. If somebody asks that for particular method, whether this method is good or the another method is good, then you have to do this comparative study, making the film by both the methods and afterwards make a conclusion out of that. So which method is best, that can also be studied by the simple way, having these films. Okay. Okay, let's forget about the other one. Okay, this is the very simple way of making the measurements for the electrochemical supercapacitor studies. And of course, probably you might having the constant current source or the battery cycler, at least in the chemistry department, because where you have some electrochemical study, you have this cell formation. You can also form your own cell. You don't have to go for a starter cell or ready-made cell. You can have the two electrodes, a anode, cathode, and a reference electrode. And the similar system can be used for the electrochemical study of your materials which you have prepared. So instead of using this one, you can put your material over here. And this is the basic arrangement for making the electrochemical study. And these are some of the formulae. I don't want to go for further. Let's go further. Okay. This is how we want to make a supercapacitor. See, this is one material. This is also another material. You can have the materials of both the types. This is also nickel sulfide. This is also nickel sulfide. This is also nickel sulfide, having a one more separator in between. And you put the electrolyte in between. It could be NaOH, KOH. And then if you look at the reactions, you will see that the oxidation will occur. And if you go for the cyclic study, this is cyclic study, voltammetry study, where we change the potential and measure the current. And you will see that somewhere here there is a change of oxidation. It is giving one electron over here, and here one electron is obtained from the other electrode, the reduction. So electrochemical study is nothing but a study of oxidation and the reduction. We want to know only these two peaks so that we can find the whole region where this cell can be operated. So once you find it, then you can go further. These are, I forget about this one. These are some of the results. Okay, I think. Okay, if you look at the morphologies, the whole IV, the charging, discharging, and other characteristics of that material depends upon the morphology. If you have different types of morphology, you will see that the results also are different. Okay. Okay. The same thing is true for the other materials also. Okay, so this is the cyclic voltammetry for what? It's cobalt sulfide. The different types of studies can be done, and from which you can also obtain the specific capacitors. In this case, the highest specific capacitors was obtained for 800 farads per gram for the film which was deposited at 353 K. So at low temperature, the results were not good, but the film, when it was deposited at 353 K, results were quite good. So probably what we will do, we'll deposit our material only at that temperature and use for our application. So that's how we can optimize it. Okay, the other things are very much similar to find out, and this also gives the idea. These are the reports from the literature, and this is where we stand in the literature survey. So we're not that much bad having the highest values. We have reached to be values near to the literature also. But our methods were simple, very simple method, which we have used for making our material. Okay, then I skip it. It's not important for us. So let's go for a little bit further. You can have the supercapacitive properties in order to decide. And these are a comparative charge afterwards. What we have here. So from the materials which we have studied over here, we study large number of materials. These are the different materials which we have studied. And these were the supercapacitive properties in terms of the operating potential, specific capacitors, all the parameters are to one side. And these values shows the highest one. So that means the copper sulfide is good. And at the same time, in the symmetric device, and if you have the manganese sulfide, this also has a good value. So one of them is a cathode material, other one is a anode material. So what we decided to make a combination of these two, because these two materials have shown the highest values from our study. So I just skip. This is also a way to make the manganese sulfide oxide film, and this is how we have formed the device. So this is a MnO2 electrode, which is a positive one with such type of morphology. This is the negative electrode to this side. It is film is formed on this side, and in between we have a jelly electrolyte. So we have an anode, we have a cathode, and in between we have a jelly electrolyte. So it's a sandwich. This the jelly electrolyte is sandwiched between anode and cathode. One is anodic material, other is cathodic material, and we have sandwiched it. And what type of device which we have formed is something like this. We have formed 5 by 5 centimeter square devices, and we have used for further applications. So this gives the whole process of making the material. This is one material. We do it on the stainless steel, which is quite flexible, because there are many applications where you need to bend your device itself so that but after bending also you should not lose its property. So we have studied at different bending angles, and this is the whole procedure that how we have made the device. We put it here, this is one side, this is another side, we paste it by the polymer gel, we put it like something like this, and you will see that afterwards we put it under a hydraulic press for some time, and then our device is ready. Even you can bend it up to 165 degree. You can bend it without losing its performance, and then we use it. These are only two cells, two devices in series. We have charged them, but you will see that it has a panel of about 700 light emitting diodes, which can light up for longer time. So these two devices, of course, this will last longer. If you charge this for 30 seconds, it can light the whole panel for maybe for 1 minute or 2 minutes, depending upon the load in the series. That depends upon the load. The discharging depends upon the load. So we have also successfully made the devices using very simple methods, using two materials, one is anode, another is cathode, putting them together, putting a polymer gel inside and pressing them with the hydraulic press and forming a device which can bend up to 165 degree. Still it gives a quite good performance. Okay, this is the performance of the cell itself, and this is also a quite performance that has been given by our device. Also, we have a range of about 2 volt. It's a working range of one device. So we operate in about 1.8 volt or so. Okay, so these are some of the results. We have studied stability and humidity and temperature impact. We have done everything on this type of devices. So these are some of the results. This is the stability study. You will see that it is quite stable. It is quite stable about a large number. About 2000 cycle, it is quite stable, which you can use it with 93% of stability. Current retentivity is there. It's 98% of capacity retention is there. And these are some of the devices which we have made a flexible solid state supercapacitor symmetric device that we have formed. And these are some of the results from our research papers. You can charge the device for 30 seconds, and this is the glow of that light emitting diode. Even after 300 seconds, you can see the discharging. You can see some of the current over there, which quite shows that the device was quite well, which is made with the very simple devices. The stability and other things which we have tried, this is a symmetric device. Now, we have also made some of the devices with the rolling using electrolyte. So this is all the material deposited on all these strips, stainless strip, and then we have rolled it by putting some filter inside and keep inside a very simple device. Of course, you know that this is the earlier roll caps which were available for the cameras. So we have used that one for making a device and sealing it, and it works. Okay. So this is the device. Of course, it doesn't work, but we have the very live demonstration over here. You can give it. These are some of the highest results which you see that about 730 light emitting diodes, which can be lit up. Of course, this is from the Shivaji University presentation, but you will see that with two flexible symmetric devices in series can last longer and it can give the glow. So you charge in few seconds, but discharge can be for a longer time, and you can glow this part. Now, where will be the applications? Of course, I'm not talking applications. You can see the light, signal lights, which has to glow for some time. So these are some of the applications, or sometimes, or they say that you can use it in the wherever electronics where small milliwatt power is required. So even at the remote places where there are some electronic devices which are used for sensing purpose, where you cannot reach frequently, you can use such type of supercapacitors, because with this supercapacitor, we have solar panel over it. The solar panel can give the charging, which can be used further for the discharging for your device. So this is also a purpose of this part. Of course, these are some of the further calculations which we have made. And these are some of the YouTubes. If you visit, if you put my name and go to the videos, we have put all our videos of our devices on the YouTube. And based on this, we submitted a project proposal to the Department of Science and Technology 1 year back. That was the Technology Translation Award based on this manganese oxide copper sulfide, for which you got the best project award, and we could get the grant of 30 lakhs. So that's project I am running. We are developing, we have gone far ahead of this device. We can make the device, and in terms of hundreds of devices we have made. Now we are making the stackings and wanted to make a bigger device. It's a bank. It will be a bank, a supercapacitor bank, which can be used for different purposes. That's what we are doing now at presently, because we got a grant about 30 lakhs just to develop this device. And we are using the very simple method. That's why I'm stressing again and again. Even I got a national level Department of Science and Technology award for this purpose. The methods are quite simple. Methods are not fancy. They're quite simple, and even you can do that. Okay. So with this verse, I finished my talk. And I thank you for your patient listening also. If you have any questions, if I am able to answer, I will do it. Thank you.
Thank you so much, sir. It was indeed a nice overview of how material science-based technology can make a revolution in electronics, and of course in the upcoming photonics, which is closely related with the physics and chemistry. Before starting with the discussion from the audience, I have two questions, sir. The first, that I'm really impressed. I know the method, that SILAR method, you developed in your lab quite a few decades ago. And still your group is working on that. What actually, why any people, a researcher get the Nobel Prize? Because they work on a thing that they invented a long time ago, and consistently working on their own technologies or innovations fundamentals. They find their own drawbacks, try to overcome them, and show them that their technology invented 20, 30 years ago can change the world. So what the Professor C.D. Lokhande doing is the same. So they developed this method long time ago, but still his group is working, and which is quite impressive. That's why he is one of the best in India. So my question, sir, with the SILAR method, which is very simple, Can we go for the automatic way? So like a robotics? that
Yeah,
can
yeah,
be
yeah.
in this
Yes,
environment?
yes, yes, we have. No, it has already been computerized. It's computer based. We, in fact, now probably you might be knowing we have 4 units. We have purchased 4 units, and there's one company, Hallmark, that is fabricating this unit. Now we have totally computerized method. We have to program it, and it will do everything. Dipping cycle, how much time it has to dip, whole cycles we can program.
Oh,
All we can program the temperature, we can stirring rate, everything can be computerized now.
so I was.
We have 4 units. We have 4 units in our lab.
I was looking the news, some companies, I think in Hyderabad, they started the commercial supercapacitor devices. I think in future, all supercapacitor methods, not only supercapacitor, but all these solar methods can be used as alternative for industrial transportation.
Yes, of course, yes, yes.
And the second question, sir, with the earlier speaker, Professor P.S. Patil, sir, emphasized that we have to go with the green approach as well, because all these elements we are using, they are heavy metals or maybe a lanthanide based, which are rare materials. So is it possible to go with some green approach to replace these materials for supercapacitor or other?
See, some of the materials can be. You can use the biosynthesis methods for making the metals, and those metals can be converted. For example, copper can be done using the biosynthesis method. Silver can be done. Gold can be done. So other methods, other metals can also be done if you know the right electrochemical potential of the system and the reduction way of doing that. Once you get that method, now we know how to make it a compound. So we also done some work long back by converting the copper into copper sulfide, silver into silver selenide sulfide, even changing the cadmium sulfide into silver sulfide and so on. So interchange can be done.
Okay.
That is possible.
Not
That's possible.
total material can be replaced.
Because when you use sulfur, selenium, these are toxic elements,
Yeah.
which you cannot avoid.
Yes, yes.
But you can reduce to some extent.
I have my one friend in Norway. They're working on the corn flowers, the waste material from this corn to make a batteries. But I think this is just a concept or hypothesis, because battery materials are also heavy metals.
Basically, what they are doing, they are making the carbon. They're all carbon based. Yeah. They're all carbon based, because when you make a combustion process or heat it, burn it, ultimately it is in fact, it is just a carbon.
Yeah.
So I think probably if you remember in 2018, we have a scientist from Korea who was working on making the carbon from the Coca-Cola. Because if you take the Coca-Cola, you will see that after some time, if you evaporate it, you will see half of the part is only the sugar. It's lot of sugar in Coca-Cola. So he was using that Coca-Cola for making the carbon material. Yeah. Another material he was talking was the bread. Even if you burn the bread, it will become a carbon. Yeah. So that was his approach. So such approach is already there. Yeah, exactly. But they are not successful because of the content inside. Because if you make a bread, we don't know what will be the next bread. Yeah. Even those who are working with the making the nanoparticles with the, say, the copper or silver or gold using biochemical synthesis methods, somebody puts spinach, somebody puts some other part, use another thing. But unless and until you specify the species, yes, and who is responsible for the reduction of that species, is very impossible. And I heard that these kind of food materials are not allowed for technological applications. Right. So like ginger or bread will be not allowed for technological applications. Right. Yeah. So any questions from the audience? We can take some 1 or 2 questions. Yes, yes, madam. Metal oxides is basically the electrical conductivity of the material. When we have the oxide, its conductivity is always less compared to the other compounds. For example, if you have a metal oxide and the same metal sulfide or selenide, the metal sulfide will give the better conductivity, electrical conductivity. And highest conductivity is required or for the supercapacitor purpose or any purpose. So that is the major restriction for the metal oxide. Otherwise, metal oxides are pretty good. Some of them, for example, the manganese oxide, we are using invariably. Now we have stopped and we have found some other alternatives for that one. That's why we have formed now a pair. We have a pair now for that one.
Hello. And another question is, sir asked about green biomaterial to interchange material. So I will ask to similar, which organic material are electrolyte?
Organic materials, see, we are using PVA, polyvinyl acetate. There are some organic compounds, but again the limitation is same one. You cannot use many because of its electrical conductivity. And basically they are costly also.
Exactly. Because organic materials, they all are based with the carbon, and the carbon has highly volatile sometime. So most of the time, these technologies like battery or supercapacitor, even solar cells, they are inorganic science because the stability of the material, decay process, and the reproducibility is higher for inorganic things. So I think, any other question?
Yes, madam.
Recently, there is now trend that is anisotropic metal chalconaires are used for the supercapacitor synthesis. What is your view about that? Is anisotropic metal chalconaires to use in the capacitors?
Which are those materials?
Cadmium sulfide or disulfide?
No.
It means that is a nanosheet preparation.
See, when you talk about the supercapacitor, the material should have the multiple valencies. Cadmium sulfide doesn't have a multiple valency. It has only 2 plus.
Multi-sheets formation.
No, multi-sheet doesn't work because the way by which the charge is stored, there is a conversion, there is a taking and giving of electron. So for cadmium sulfide, there is not a for higher state. Cadmium always exists in the CD plus 2 only. So cadmium sulfide, cadmium selenide cannot be used in the supercapacitors. The manganese sulfide has the 7th valencies. So it can exist in all. So where in our case, there is a always transfer of electron between Mn plus 2 to Mn plus 3. For cadmium sulfide, nothing is like that. So that cannot be used. So this is the basic requirement of the materials. So all materials cannot be used in the supercapacitors.
Exactly.
Because they don't have the multi-state, multivalent states.
So thank you so much, sir. It was indeed a great talk and something informative me too, because I have physics background, but first time I understand about the supercapacitor. So might be this will be some calling stone for me as well to learn physics again. Thank you so much, sir. And we'll forward for the next session. Thank you.
Thank you. Thank you, sir. Thank you.
Thank you very much, sir, for giving a nice talk, Dr. Professor C. Lokhande, sir. Thank you very much. Also, thankful to Dr. Nana Sahib Thorat for chairing the session. Thank you, sir. Request to Dr. Nana Sahib Thorat for talk. I request to Professor Dr. Rizado, sir, for chair this session.
Dear friends, we have with us today Dr. Nana Sahib Thorat, a leading scientist who is working at Medical Science Division, University of Oxford. And as I have told you earlier, he belonging to mining. And though I have read his biography, I will again a few things about his research. So I think day before yesterday, he had interview with Sahyadri Vahini. And in that lecture, he had informed about COVID-19 and some deaths. The person suffering from cancer, diabetic, and they have taken international survey regarding what's the cause of COVID-19 effect and so on. So it was very interesting, and I hope with his today's talk, definitely you will be getting much insights. What are recent advancements as far as research is concerned? So I request Dr. Nanasaheb Thorat to deliver his talk.
Thank you so much, sir. Understand all you are waiting for your lunch time. And actually my talk was planned after the lunch, but due to some last moment meeting with some of the higher authority, I have to go. So I'm really apologize for that, the inconvenience for you. I will be taking a long time. I will try to submit my presentation. So my presentation will be in three parts. One is the how physics is used in the biology, simple formula, how material science makes the interface, and then I will come with the biology work that we are doing, and then I will come with how we transferred, or I transferred from physics to medicine all the time. So currently I'm working at the Medical Science Division, Oxford University. You might heard about the Oxford University because of their breakthroughs in many technologies. So it's world's one of the best institute for many technologies, including one of the recent technologies, the vaccine. So this is the aerial view of the university, Oxford University and Oxford City as well. So because we all have campuses, mostly India, South Korea, US or Japan, China. We have universities somewhere outside the cities, but most of the European universities, they're always in the cities. So we call it as the city in the university and the university in the city. So this is the main campus. We have more than 6 campuses, some hospitals and all this. It is one of the oldest university in the world. Almost 1,200 years ago, they established the university. We have academic curriculum, research profile. So not only just making scientists or students, they create the future leaders as well. So most developed countries are those around 40 prime ministers were educated from Oxford, including so last 20 prime minister, they were from UK. The UK's prime minister, they were from Oxford. So the recent one, Mr. Rishi Sunak, he is also the Oxford alumni. So when they have the first year induction, they always announce a future leader, future prime minister is sitting here. He may be a prime minister of any country in next 30 or 40 years. So they make the leaders as well what the universities have to do. Search. Start. Search funding degree from the different agencies, international, national agencies. Also, I would like to acknowledge another funding agency who is my bread and butter actually is the European Commission. European Commission is the bureaucratic body of the European Union. European Union means it's a group of 28 countries, including Germany, France, and all these. So they have strong research funding. I time this commission. Just talk how physics, material science, and this can work for the sciences or the better purpose of humanity. So, the first species in the evolution theory, if you go through the Darwin's evolution theory, this first species was in the sea or ocean. So why? So there is interaction between the sunlight. What we had that time. It was just the sunlight over Earth. Earth constitutes some ground that have minerals and soil, water, hydrogen, so between soil created the first species. So that's why the light is most important in our life, because this interaction because so our body is 90% the light. Even so it is like a gases or light. So it is an interaction of the light with the materials gives the many interesting phenomena. So as a physicist, chemist, even light, they have two theories. One is the electromagnetic wave theory, it is something a wave. But another theory is that it has a photons. And both theories are correct. So this and light is a wave. So if you use light, it's depend on our So if you want to use light as a energy, it comes from the sunlight, that is the source. So involves synthesis by plants. And of course, when we talk about the market, it is a $10 billion, sorry. So it is the third, we-fold higher number in India's total GDP. This is what the market right now for the light. In COVID, you have seen these RT-PCR and all these techniques, they are light-based techniques, especially laser. So it's photonics, that is means the science of the photo means light. It has a rich history from 17th century till people are working on that. Also engineers and biologists. And it has a bright future. So when we compare the light, electromagnetic spectrum, it consists from the X-rays to gamma or to the infrared rays. So light spectrum for different applications, communications. Suppose we want to see something inside our body, X-ray. So that is what the spectrum. So they are energetic, but how so both spectrums are equally important for our applications. So we basically work on the cancer-related field and others. So it's kind of medicine. So we use the light for medicine by bleaching the materials. So we need a brief between that because so what we do, we actually use the light for materials for healthcare. So maybe this is a very basic physics theory. We know the scattering process, absorption process, reflection, refraction. I'm not going into that details. These all processes, I was on occasion, why we learn scattering and where it is used, but it is used every day. So scattering is used in the diagnostic and imaging like X-rays or maybe so they all are based on these theories. Of course, there are some interaction like absorbance or emittance by the materials. And that is what they use for theranostics, means therapy for healthcare. So it may be a cancer or other diseases, even COVID too. So how it works? So when light interact with the materials, it might be absorbed, it might be reflected. And every material has their own properties. Absorption index for all materials, including water and others. So we can choose which material solving which is the best way. And this is what the chemistry of physics. Every electron element, when it excited by any external energy source, electron goes in upper energy level, then it comes down, and during that it releases the energy. And that energy can be used for many purposes. So the simple phenomena we use for applications. Why we are on cancer? So you know, the COVID came in 2 years and gone. Well, this is the infectious disease, or it's kind of a disease which has a very small lifetime. While cancer has 1,000 years of history and maybe remain for maybe a couple of years. So when we talk about the physics, biology, connection between the living. So physics is energy. So it might be a light is energy, magnetic field is energy, ultrasound is the energy, even electricity is energy. So we use that energy for our own purposes. So similarly, we use the magnetic field to heat the materials so they can kill the cancer cells. In the same way, we use the light to heat the material as well as make reactions. That is called the photodynamic therapy. And electricity as well, ultrasound as well. Ultrasound is very well known technology used in the day-to-day life. So again, I'm coming here with the first slide, but what form of energy we are using? Suppose like for the healthcare, it may be energy, it may be electromagnetic radiation. So it depends on your application, what form it will be. Suppose we have to use it for diagnosis purpose. Most of the time, it is a electromagnetic wave, and for therapy purpose, it is a photon, means the particle. So we can see with the some near infrared light, visible light, UV light, and all type of therapies we can do, not only for cancer, but other diseases as well. So how it interacts with the matter? So matter means some material. So let's give one example, gold. Gold is very famous material. It's crazy about the gold. Scientists and it's a highly active material. Some conductors still hinting that we need higher surface area for higher reactions rate. So the similar, like if you go in the nano scale, gold has the higher surface area, so it can interact more and more with the light, and that gives the more properties that what we need. So when a small gold material, suppose excited or kept under the light, it can absorb the light. Let's say from 5 nanometer to some 100 nanometer, their absorption pattern changes. So this absorption pattern is when you go down, the properties of the material changes, and we can pick up one property for your own applications. Some non-plasmonic is called a plasmonic material. There are some non-plasmonic, they are not light activated, but we can make hybrid compounds, two materials together, and they can be light activated. So some materials are still used, but they are inorganic materials, some lanthanoids, which are toxic, because when we talk about the healthcare application, the first thing comes, that is what is the toxicity. Toxicity means their reaction with our body or cells. So we have to think about green, not green, but biocompatible approach in the life sciences. So these materials are mostly very toxic, so not very famous. Very recently, some of the group in Oxford, they work on some new technologies which can give you the, in daylight, just you can walk in the daylight with some materials. The reaction can be triggered in your body, and that can act as a self-healing. Suppose you have some disease like a diabetes, just walk in the light with some drug, maybe something light activated, it can cure, it can reduce the sugar level in the body. So this is the technology coming with this photonics and light activation. So sugar problem. Taking the for that, we decided to find the kidney or maybe heart. So we have to reduce that. And that's why some technologies are coming. Another technology is very interesting. This is from the USA, developed very small optical fiber, which can map the tumor inside liver in animals. And that mapping can give the exact tumor nature, where is the cancer, how big it is, and how we can diagnose it at an early stage.
Also, they diagnose using the light, the neurons, means the brain neurons, it is the connections, electric signals, they pass electric signals. They act as a memory, they act as a locomotive for our body. So they activated the neurons as well using the light. There is a new generation implemental healthcare devices which can give you your sugar level. Now for sugar level, we have to use some injection, take the blood and then monitor it. But we can monitor the blood pressure without that, or maybe the weight and all these, but not sugar level still. So maybe a technology will come that will give you the sugar level easily without giving any injection or taking blood from the person, or some other information from your body, your liver is functioning well, its kidney is well, because for that we need to take all blood tests, urine test or other tests, MRI, CT scans as well. So these kind of photonic devices are replacing these highly sophisticated devices. These are called the wearable technologies. So you just wear a small something like ring or maybe your watch that will give you all information about your body functions. Some are smart watches that gives you some information, some BMI index or maybe some your blood pressure, heartbeats, but not some other like how your liver is functioning, how your kidney is functioning, how is your sugar level. Its cancer is developing in your body. But it will be a future technology, maybe in 10 years, 20 years, it will be marketed, but people are working on that. So what we are doing actually, it is simple research we are doing even in Oxford. So we recently got one award for the very, very novel but simple technology for breast cancer in women. So breast cancer is one of the most dominated cancer in women after the heart strokes. And it has a 10 molecular subtype. Actually, right now it has a 40, means a single breast cancer. Every patient have different type of breast cancers. So we have to use the different drugs. And that can be a difficult because not all patients can be treated with the same drug. We need new drugs because cancer is different for everyone. And many other factors as well. Right now, all diagnosis depend on the chemical and biological methods. So what we did, we developed a simple laser-based device, which based on the gold materials, magnetic and gold materials, and when placed under the light, they heat and they kill the cancer cells in laboratory. And not only in laboratory, but we tested it on the animals, especially a rat and mice. We worked with one of the world's top hospital, animal hospital in Switzerland, Zurich. So you can see that material, the plasmonic material, which has chemical functionalities. And you can see one image where blue, green, and red dots. So green means the cells, cancer cells, they are alive, they are healthy. And the red means they are died. So if you use
Laser technology, let's say for 30 minutes, you can see all green goes and came into the red once all cell dies. Well, this is a simple information that we, because you mostly people are from physics or chemistry backgrounds, they don't understand what to do and what is good. What another technology we are developing, that is light activated nanocapsules for infectious disease. So infectious means what? It is came from the viruses or bacteria. So COVID is infectious disease. So COVID comes through the communities. But there are other diseases as well, bacterial infections. And for that, we don't have any option. We have some antibiotics, but use of antibiotics makes failure, kidney failure, and other failure. So we recently developed a very small capsule in the laboratory, activated under the laser light. So they make a heat, and when they heated, they can kill the bacteria. And these are not simple bacteria; they are very, very dangerous bacteria. I think it is not allowed to work on these bacteria in India. So they are very sophisticated bacterial labs. We work in Korea and Poland. So this is what the technology we are doing for the transfer. So we have commercialized this technology for hospitals. And the company from Finland for agreement with us. So what we are doing right now, very interesting, because we are developing some materials, that is gold and magnetic both together. Very simple chemical reactions, developing very small materials, around 20-30 nanometers, so they can go into the brain, deactivate or they kill the brain tumor. So right now, our cancer research is in the laboratory with the 2D surface to cells and then goes to the animals. And the animals has a problem like mice and rat. We can induce cancer into them, but that cannot be compatible to the human because rat, mice, their anatomy, physiology is different and human is different. So all these models get failed when technology transferred to the human. Only 5% success rate when you transfer animal into the human. So now the technology is coming. You can develop the models in the lab. So they are equivalent or far better than the animal models. So we are developing models. So we can bypass the animal studies. And right now, many governments, they are against the animal studies for that. Mice or rabbits or dogs, they are not allowed right now. So for that, we are developing technology to make all good and chemically activated materials under the light to deliver the drug first and scale. So this you can see the range, but it's not
exact itself, but this is the drug right now. So doxorubicin, which is the chemotherapy drug used for the cancer patient. So it is actively delivered under the laser light and by the nanoparticles into the cells in a compact 3D tumor. And not only on the, because 3D tumor means it is a spherical or maybe something higher surface. So when you treat them from the above, you have to monitor is really a drug going into the down and down. So we use the light and magnetic field to gauge higher concentration of this drug and materials into the tumors.
also this here you can see this green turning into the complete red. This light tumor is going to die in a short time, 48 hours, with different cells. So that UX7 means it is a brain tumor cells from the adult patient. These KNS and RES, these are the brain tumor cells from the small children. So our group is working on the small children cancer. And right now we are working on cancer because we in the last stage cancer due to the breast cancer. So we are working on vaccine recently got the clinical from Irish government against the this kind of cancers. This one is kind of like some flow cytometry result. Here also we use light because it is all mapping of how many cells are died, how many are still alive, and it is a quantitative. Well, now I will sum up with my research because it takes time. So actually I transformed from physics, quantum mechanics to the mathematical physics to energy science to the medicine. Now I'm closely affiliated with the which is means everyone has a problem with pregnancy. After pregnancy, they have pregnancies, they have consequences with that field, and our department is basically that. We research on cancer in that department, not with directly, but we associate with these humans who has a problem. So this is what the from physics to the medicine, which is quite difficult. Even doctors cannot do that. We need expertise, ingredients for knowledge. So I started my just simple 12th physics, chemistry, biology. I don't have too much craziness about the biology, and then I choose my master's. Even I have less score in my 10th and 12th, and high score in biology, but I removed that subject during my BSc and I choose electronics. Even chemistry was not my subject. And went into the pure physics because I was crazy about that. But accidentally I came into the PhD and my supervisor advised me to go into the biology. So you will have great future. So he realized that 10 years, 12 years ago. That's why we need a good supervisor during our PhD and research who can map your future and career. And so 12 years ago, he told me that if you physicist go into biology, you will be a great successor. So then I started my first independent position in South Korea, especially in the Medical Research Institute. and working on the cancer and bacterial infections. But here are most of the doctors, biochemists, microbiologists, protein chemistry people, biochemists mostly. While my second position in Ireland, it is in the physics department, but we are working on the same problem. So the environment is different right now. Here we are surrounded by the physics, chemists, pharmacists, people, biomedical engineers. So we can get the different skills in different institutes, but the research is same. In fact, when I got my first European phase of PhD, I was in Poland and Switzerland and hospital in Zurich. So we are working on the animal experiments. I met some psychologists. They are not human psychologists, they are psychologists for the dogs, horses. I made the radiologist, MRI, I see it is not for human, it is for horses. So their patients are the horses, dogs, cats. So I worked in that hospital for almost 1 year. And then I moved to the Oxford in a different area on children cancer issues. So this is our project, which is recently finished, and we stayed. So that we are using technology the cancers, not only kill the cancer, but surgeries, doing surgeries. So I'll skip that. This is the last part. So how we can commercialize from basic research to the technology support system. So we have a commercialization team from different institutes. And it was our institutes who supported me for that. We have technology transfer unit, commercialization unit, marketing unit, fundamental science unit, patent unit. Also, we have plan for that as well. So making a laboratory scale research into the market. So we need to and ideas as well. And of course, a good framework. Without that, we can't commercialize or can't commercialize the technology from laboratory to the patient. So we have every institute, like in Oxford, we have 7 technology transfer units. So we are supporting every week spin-off. So every year, around 52 new spin-offs come from Oxford. And they are functioning, not just a spin-off on paper, but they are functioning with capital and with the buildings and all this. So this is my last slide. I should have to thank all these guys, collaborators from different institutes around the globe, from US to Europe to India as well. Collaborators from different institutes. Mostly we have collaborators from 30 countries. And with this, I'm going to stop for today. I hope it is not boring and long. Thank you so much for your patience, and you can take some questions if chair allows. Thank you so much.
Thank you, Dr. Nanasaheb Thorat, sir. It was experience to listen about your innovative research work, medical research work. You have spoken about the first species from ocean. It has been evolved. But I think the urase experiment, many biology students or chemistry people, they might be knowing. The amino acid were the building block for making of life. And I think glycine was the first reported amino acid who had formed on this earth to create new forms of species and so on. So you have also talked on recent clinical PTT, PDT, and we made familiar. Actually, I don't know how much we have grasped in 3D brain tumor concept and so on. So, sir, here there are my MSc chemistry students. They are doing in analytical, very small research projects. They are also dreaming to become like you. So what advice would you like to give in this regard?
I think in research, we need not clever student, but we need a student who has a patience for research. So I always advise those who have highest score in their 12th, don't come for the research, go for engineering, medical, because society push you. You are very clever and you can make money by doing engineering or medicine, make money, no worries. Sometimes there is a different world as well. And that world comes not only with a 1 night, 1 year journey, it takes a long time. So my advice is, if you are passionate about the research, go by one step to next step to next step. You can watch the big hill or the mountain or the Everest, but you cannot go every time there. Every day there. You have to walk on one foot and then one step and next step and next step. The same happens with the research.
The problem with the cancer, it is not a disease. It has a brain, it has a decision-making power, other diseases don't have. And that's why it is quite difficult to treat them. Not a single scientist, it may be Ayurveda, it may be a modern medicine, who claim that, oh, we treated the patient who totally vanished the cancer. Once you have the cancer, means it is a lifetime for you. So people are working on cancer vaccines as well. So similar like COVID vaccines, the COVID vaccines or other vaccines are different than the cancers because the vaccines is for to prevent the disease. So suppose you have COVID vaccines, means you don't have to be a COVID disease. While it is exactly opposite for cancer, once you have the cancer, then we can develop the cancer vaccine to stop the cancer. So this is what the difference. Maybe next 5 or 10 years, there will be some vaccines for cancer patients. There are news in media that some are developed cancer vaccines, but not a single cancer vaccine in the world is marketed. These are the vaccines against the HPV vaccine. You might know, especially this virus makes a cervical disease for women or maybe oral disease for men. So the vaccine against HPV can prevent the cancer, but it is not a cancer vaccine. There is another vaccine called the hepatitis vaccine. Hepatitis it is another virus which can kill the liver cells, and then we can get the liver cancer. So there is a vaccine for hepatitis, but it is not cancer vaccine. But there will be a future instead, and hopefully in other medicines will follow that. Ayurveda is preventive medicine sometimes. So it's not a medicine, it's not a therapeutic, it is a lifestyle. It is your food as well. So what you eat means Ayurveda. See, the Japanese people, they can live for 100 years, but they don't have Ayurveda. They eat fish, they eat juice and soups, but they live for 100 years. Europeans, they live for 80 years,
but they don't have Ayurveda as well. So they have their own natural medicine as well. So Spanish medicine is there, Portuguese are there, French, they have their own medicine. So every natural medicine can be used for many diseases. Yeah.
Afternoon, sir. You told in one interview that in the next 50 years, all people over the age of 40 will have diabetes and 1 in 6 will have cancer. What would cause that and what can we do to prevent it from happening?
Yeah, thank you. So I think you have watched my interview. So not all the people, but there is a certainty that out of 6, 1 will be get affected with the cancer and 1 definitely with the diabetes. So now India's current rate that getting the diabetes is around 40 years. Earlier it was 60. And the cancer is around 50. Sometime comes to 40 as well. So to prevent it means make awareness about disease, why we get that diseases, what follow, how we can eat natural things, exercise, healthy lifestyle. That can prevent all diseases, not only cancer, but diabetes and other bacterial infections. We don't need immunity booster or others, that is a marketing players, but we need a healthy lifestyle. And for healthy lifestyle, we don't need special consultant and doctors. It is healthy means you have to follow something that your grandfather or grandmother were following. So that is what the healthy life. So healthy life is the best medicine or the cure for every disease.
And so cancer is not completely eradicated. It comes back after some time and the person's to die. Then my question is, can cancer be eradicated completely?
Yeah, that's why people are developing the vaccine. So once you have the cancer, it comes back again. So we have to prevent. So that cannot come again. So when someone has a cancer, give him a vaccine, her vaccine, then it will not come again. So that is what the activating our immunity against the cancer. So that is what the natural therapy. So maybe it will take 10 years, 20 years maybe. We need huge infrastructure, funding, and all these things for that kind of highly ambitious project. And so just one moment, you told about people don't understand what the 3D models. I will give them an example. Right now, we have many problems when any drug comes from any company or university for the market. They have to do the clinical trials, phase 1 to 3, means first trial on the human, it is toxic or not, then it is activating immunity or not, or it is curing disease or not, how much percent it is in clinical 3 stage. But there is a resistance against people. They are opposing for such kind of clinical trial. They don't get many patients. So some companies are now creating the artificial human in the lab. So they can do the clinical trials on that man, woman, or maybe a child as well. So some companies, they are making the small child in the laboratory who has all features, anatomy to the psychology of the human. So we can do the clinical trials on that child, and which is 100%, not 100%, at least 99% accurate to the human. So this is ambitious project of people working. We are starting one of them, but creating such tumors in the lab. So we can treat, we can give the all data in the lab. So we don't need to go to the human directly. The lab data can be used to treat the humans. So,
nice information and interdisciplinary research presentation, sir. What I know is cisplatin is the first cancer drug used in pediatrics also, and as you said earlier in your presentation that there are some electrochemical devices which are fitted in our body and which can like pacemaker and all.
Yeah.
Is there any other metal rather than palladium and platinum? Of course, ruthenium is also there. But is metals like cobalt, which shows both properties like energy transfer as well as electron transfer, are used in such type of medicines? Is there any? This is out of curiosity. I'm asking.
Yeah.
Is there any attempt going on for trying other metals?
Yes, even we are trying magnetic materials. It's cobalt ferrites, copper ferrites, or manganese ferrites, in lanthanum ferrites, iron oxides, all these. But the problem I mentioned that they have toxicity. Cobalt is highly neurotoxic, manganese is highly neurotoxic. They can kill the blood cells most of the time. So we have to screen out first their all toxicity profile, and then how to check, is it really feasible for the humans? So every time when material scientists, physicists make some new hypothesis, doctors opposes for that because they say, oh, this is toxic, it will not work. Similar happens with the X-rays. They says X-rays is not for human, but every doctor now in the world making money from the X-rays. The same happened with ultrasound. They oppose that technology. Now everyone has that business model. MRI, CT scan, they are opposed by doctors as well. Now many technologies coming based on nanomedicine. Doctors are against that because it will not work. But now in next 10 years or some vaccines that actually not rolled out in India, but Pfizer and Moderna vaccines, they are nanomedicines. And probably in some, even this Covishield has a nanomedicine as well. So next couple of years, these nanomedicine technologies will come. So we are using gold-based materials, which is metal, inorganic, toxic, of course. Gold is shiny for body, but it's toxic for the cells. If it is higher amount, every material, even our food is toxic if you take it excess. So if we want to use such kind of materials who has many physical properties, we have to check the biocompatibility as well, complete profile.
So I think, is there any question? Okay. So thank you, Dr. Nanasaheb Thorat, sir. It was very nice experience. I was also very much curious to listen personally because of Doordarshan publicity and so on. Here also got few brochures of Oxford University Press. So shall we distribute to 3 brochures?
Yeah, that is for faculties or some students get interested.
So I will hand over it to. And I think according to organizers, half-hour break has been given, and later on again we have to gather here in this hall. Thank you very much.
Thank you very much, Dr. Nanasaheb Thorat, sir, for giving a very nice talk. Also, I'm thankful to Dr. S.D. Jadhav, sir, for chair the sessions. So 30 minutes for lunch break. So come back after the 30 minutes. Dear participant, hello. Dear participant, you have to come back at 3:30. Okay. The next session will be start at 3:30 exactly. So you have to come back at 3:30, and please, for particular for MSc and BSc student, please do not leave the campus until the organizer permission. So please come back at 3:30.